Hello everyone again. This is lecture number 8 from the chapter System of Particles and Rotational Motion. In the previous lecture, we have started with the discussion, most important discussion, that is of moment of inertia. So we understood basically what is the analogous of mass in rotational motion, uh, which is basically your moment of inertia called as I. Let's look at the forward discussions regarding this topic and then move forward. This is lecture number 8 from the chapter System of Particles and Rotational Motion. I am Samir Lawankar. Let's begin our discussion. Okay. So currently we are on the ninth subtopic, that is your moment of inertia. So before that, let us do a quick revision of all the concepts we have already studied. So we have started with the introduction. In introduction, basically we understood as in what is your translation motion, what is your rotational motion, and what is your translation plus rotational motion. In center of mass, basically we have understood in vector form we can write the center of mass of a system of particles is nothing but equal to integration of 1 upon m into what we can say. Let's say first of all, let me write it as your center of mass for the normal particles. So we know that mass, let's say, how should I convey you? So basically it is nothing but 1 upon n into summation mi into xi. Correct? So let us say this is for the center of mass of particle in x direction. Similarly for y direction, what we can write? We can write again 1 upon m summation mi yi. Okay, and similarly for z direction, what we can write? We can write 1 upon m summation mi zi. Correct? So similarly, what we can also write in the similar terms, we can write for the vector r, it is nothing but equal to 1 upon m is equal to 1 upon m integration mi ri, okay, dr. Okay, so that's our basically not mi ri, it's mi dr. Okay, so that's how you should understand this complete configuration. So moving over, then we understood in the motion of center of mass basically. So in motion of center of mass, we understood. In motion of center of mass, we understood basically that your complete mass into, let's say, I write it as mr basically is nothing but equal to m1 x1 or basically mr1. Okay, so it's m1 r1 plus m2 r2 and so until your m and r. Okay, so when we differentiate it once, we'll get m into v is basically equal to m1 v1 plus m2 v2 and so until your m and v. Similarly, if we differentiate it again, we'll get total mass into acceleration of the center of mass is equal to m1 a1 plus m2 a2 and so until your m and a. Okay, I hope this thing is quite clear to you. So basically after this, what we got, we can basically write this m1 a1 plus m2 a2 as nothing but equal to capital M into a is nothing but equal to f1 plus f2 and so until fn. And we know that every force is basically a summation of your external force plus internal force. But according to the Newton's third law of motion, F internal is equal to 0. Therefore, we can write mass into acceleration is nothing but equal to summation F external of all the system of particles. Okay, fine. Then in the next concept, we understood about linear momentum and also we understood how the linear momentum is conserved. Then the next concept of vector product of two vectors. So in vector product of two vectors is basically considered that A cross B is basically equal to, so basically you need to understand two different concepts here. The first was regarding magnitude. The magnitude is equal to magnitude of A into magnitude of B into sine theta, where theta is the angle between A and B. And what is its direction? So we will find the direction basically using the right hand thumb rule. Basically, if this A and B are in one plane, then this C will be perpendicular. If this is equal to A cross B, it will be perpendicular to the direction of A and B. Right? Direction can be used or calculated using your right hand thumb. Right hand thumb rule. So in this concept, we also understood different properties of your vector product. So to understand it again, you can just refer back and understand that complete lecture on vector product of two vectors. Moving forward, we understood about angular velocity basically. So we understood omega, we understood about alpha, then we understood about torque, and we also understood about angular momentum. Right? In the seventh concept, then the equilibrium of rigid body, we basically understood that for the equilibrium to attain, we will basically do translational equilibrium and rotational equilibrium. So for translational equilibrium, what is the equations required? So for translational equilibrium, okay. So for translational equilibrium, what do we require basically? We require that summation of fx is equal to 0 and similarly summation of fy is equal to 0. Okay. Similarly, what we can say for rotational equilibrium? For rotational equilibrium, we can say rotational equilibrium. So for rotational equilibrium, we can basically say that the summation of all the moments about any point, let's say I write it as some point A, it should be equal to 0. Okay. I hope this concept is clear to you, as in how we are trying to find out or how we are trying to do the equilibrium of a rigid body. Right. Then the last concept we understood about the moment of inertia, and basically understood that it is nothing but denoted by I. So we can basically write di is nothing but equal to dmr. Correct. So this was the final concept which you understood. Let's now move forward with our further discussion. So moment of inertia. So before going to the moment of inertia, let's do a quick revision of the analogy between your linear motion and rotational motion, or basically translation motion and linear rotational motion. So translational motion, and second is your rotational motion. Okay, so in translational motion and rotational motion, what we can basically say that first of all we understood velocity here, which can be understood as omega here. The next thing we understood as acceleration here, which can be understood as alpha here. Then we understood, so v is okay, alpha a is okay. The next thing we understood as force here, which was torque here. The next thing we understood was linear momentum here. We understood this concept as angular momentum here, right? And next thing now is m here, which we understood here as I. Okay, so I hope this concept is clear to you, as in how we are going forward, right? Please remember what is tau. Tau is basically r cross f, and basically what is l? L is basically l cross p. R cross p, right? So moving forward, so that was the complete revision. Now let's go on to understanding moment of inertia again. So in the last concept, we have already devised this complete formula. So basically what is I? I is basically summation of i's front to n mi/r/I square, right? And we basically get the rotational kinetic energy is equal to half I omega. Okay. That thing being said, basically we found out that I is nothing but the rotational analog of mass. Okay. Fine. So all these things are clear. We also understood basically the understanding this calculation of moment of inertia for all. Let me revise this again, and then we can move forward with today's different results for moment of inertia. We'll try to calculate each and everything which is written in the table. Will not go with cylinder. Rest all we'll try to calculate. So the first is done. 3 are remaining. We'll try to resolve or basically derive each of those using integrations. Okay. Okay, fine. So let me first revise it. So basically what I was saying here was that there is a thin rod. As you can see, this is a thin rod here. So this is a thin rod, right? And we can basically say that it has a length L. It has a length L. So I'm not trying to write anything, so that I will just try to use, okay. So there's a length L here, right? And so basically if the axis rotation at the center, what we can basically say that this is your L by 2 on this side, this is L by 2 on this side. Okay. Now let us take a dm mass, very small dm mass, which is situated at a distance r from the center axis of rotation, and basically has a length which is dr. Okay. So what we can basically say, we can say that what is dm? Dm is basically mass per unit length into how much length is being covered. Dr is covered, so it's mass per unit length into dr. So I hope this is covered. I also tried to make you understand using the unitary method also. So if length covers total mass m, then dr length will cover m by l into dr. which is basically your dm. Okay, so now we know basically what is di. Di is basically dm r square. Integrating on both sides, what we will get? We will get I is nothing but equal to integration r square dm. In the place of dm, we can write m by l dr. Right now, as m by l is constant, we can just to take it out. What is the range of your dr? R, as you can see clearly here, r varies from minus l by 2 to plus l by 2, so that the complete range is over. Right. So therefore, we will just write minus L by 2 to plus L by 2 here, and just simple integration. So r square dr integration is r cube by 3. Simple rule of integration is being used. And then simple analogy, or basically values of L by 2 and minus L by 2 are put. And then when we do the mathematical calculations, we will finally get the answer of I is equal to ml square by 12. Which is also written here. As you can see, this is also written here, which is equal to ml square by 12. What is the axis? Axis is perpendicular to the rod at width. Okay. So I hope the first concept of calculation of moment of inertia of a thin rod of length L is clear to you. Now let us try to calculate another moment of inertia. Let us first do a simple one. Let us try to calculate the moment of inertia of a thin circular ring of radius r. Okay. So let me just write. So it's a thin circular ring of radius r, or let me write it as capital R, because this will make a difference when we will try to use for infinitesimal substances. Okay, so let me use it for this one. Okay, so let us try to calculate the thin circular moment of inertia of a thin circular ring of radius r. Okay, so how to do it? First of all, let me make a quick diagram. So let us suppose this is that ring. As it is thin, so therefore the amount of thickness is very, very small. Let us suppose that this is your axis of rotation. This is how it is rotating. Okay, now basically what will happen? Let us assume that this is that mass dm. Correct. Now what is its location from the center of axis? It is basically r. If you can see very, very clearly, right? It is at r. Okay, so if it is at r, what is basically di? What is di? Di is basically dm r square. Correct, it is dm r square. I hope it is okay. But here, what is the value of r? For every dm, the value of r will be small r will be capital R only. Correct. So let me write it here. For every dm, only in this case, okay, for every dm, small r is equal to capital R, because every mass dm is located at a distance of capital R from the center of axis of rotation. Therefore, what we can basically write, we can write it is equal to di is equal to dm r square. I hope this is clear. Now, if we integrate it, so it's di, and also integrate it, it is dm r square. Correct. As r square is constant, we can take it out. It is equal to integration of dm. What is integration of dm? Simple. It's capital R. Okay. We can also put the values of your what we can say limits also, but that is not required, as we directly know what is the complete integration of dm. It's m1. Therefore, we'll get I is nothing but equal to m r square. Okay, so that is how you understand this. Sorry, that is how you understand the moment of inertia of a thin circular ring of radius r. Okay, fine. So basically, we have understood this concept. We have understood this concept. Okay. This second concept will be understood in subsequent classes, when we will understand some of the theorems which corresponds to your moment of inertia. So just sit back for some time. Now let us understand this fourth one, which is your circular disk of radius r. Okay. So I hope I made it quite clear how we got the moment of inertia of a thin circular ring. Let us now understand the moment of inertia of a disk. Okay. So basically, what is the difference between what is the difference between your disk and your ring? So ring, the complete mass is situated outside only, but in a disk, the complete mass is situated all over the complete area. So basically, area is being formed. Correct. So that is the difference. Now let us see how we will basically derive this form. Let me first write. So it's a circular disk. So it's a circular disk of radius capital R. Okay. So Let us try to calculate. I would highly suggest you to try to, after the completion of class, try to solve these derivations by yourself also, so that you can understand integration at a much more detailing. uh, Integration and differentiation may be a new topic as far as class 11th is considered, but this is very very important in all the concepts of your chemistry, or some of the concept of chemistry also. In mathematics it is important for calculus, and in majority of the topic it is also important for your physics. So that's why I highly suggest you to try to do these integrations on your own, so that you can understand basically what is this dm parameter, why we are taking a dr value, what is this small r, etc. Okay, fine. So let me first make a quick diagram for this. So let us suppose this is that value of a disk. Okay, it will be having some value of thickness also, right? Let us suppose this is that omega we are talking about here, correct? So let us say this is that omega. Right, now let us look here very carefully whatever I'm writing. Okay, so we know that what is di. Di is basically dm r square. Nothing wrong in this, correct? Okay, fine. So now let us suppose, let me write here. So we know what is dm, or basically what is rho. Rho is basically mass upon volume, correct? So basically what will happen, what will be your mass will be basically rho into volume, correct? So what will be your dm? So dm will be nothing but rho into dv, correct? I think there is nothing wrong till writing this value, correct? Now let us calculate the volume of disk. Okay, so if you look clearly, or even this volume of disk is basically, let us suppose I write this small thickness is h. So this takes place as a very small cylinder, and hence what we can write, basically we can write volume of disk is nothing but equal to your pi r square, or basically if we are taking very very small r, because that will make a difference, so it's pi r square into h. Okay, because we try to take it for very small r first of all, and then we try to increase our radius from 0 to the value which is required. So let us say we are taking a very small disk here like this, okay, for which you are trying to calculate the value of your disk. Okay, so this is v basically. So what will be your dv? So dv will be basically your, just simple differentiation will give you 2 pi r dr into h. H will also be there. So 2 pi r h dr. Okay, fine. So if dv is known, in the place of dm, I can write this. So it's nothing but dm is nothing but equal to rho multiplied by 2 pi h r dr. Correct? So I hope the concept is clear till now. Now let us try to put this equation number 1 into this equation here. Okay. So if you will do this, I hope this is clear till now. I will again revise so that the concept is clear. Let me first derive it and then we can move forward. So basically what I can write the integration of this di is basically I. Well, let me write it like this one. So it's di is nothing but equal to integration of rho into 2 pi hr dr into r square. Okay, so as everything which is constant can be put forward outside, so therefore let us put first rho outside, which is equal to integration of 2 pi h in brackets into r cube dr. Okay, what will be the limits here? As I already told you, as you can see this small r here, this small r is basically will go from 0 to capital R, and hence when we'll try to cover this small cylinders infinitesimally, we'll get the complete moment of inertia, or basically we will complete the entire summation of all the system of disks. Okay, therefore this will be from 0 to capital R. Fine. So what will be integration? Basically it is nothing but, in the place of rho, I can again write it is nothing but mass into velocity, volume, into nothing but 2 pi h can come outside, so it's nothing but 2 pi h integration of r cube dr from 0 to capital R. Correct? So now in the place of what we can write, in the place of v, capital V, I can write basically it is nothing but equal to pi r square h. That is the complete value of volume into 2 pi h, right? If you see this equation clearly, integration of r cube dr is nothing but r to the power 4 by 4. And as it is going from 0 to r, I can directly write it as r to the power 4 by 4. Right? Let us deduce the things, eliminate the things that are not required here. So if you do it correctly, finally you will get the I value as nothing but equal to m r square by 2. Okay, so I hope this is clear, as in how we can calculate the value of moment of inertia of a circular disc of radius r. Let me again explain you, because these are very typical concepts. So basically what I did, first of all, I wrote the differential form of your moment of inertia. So this is the formula we know. How we know? I think so. Nothing. So this is just your summation form. So if you write this in integration form, what will it will be? In the place of mi, it will be dm. And if we integrate this basically, okay, r square. So that's how this formula came. Fine. So these all things are completed. Fine. Yes. So now di is nothing but equal to dmr square. Right. Now we know what is rho. Rho is basically mass by volume. So in the play, we can also write it as mass is equal to rho into volume. If we try to calculate the same thing for a very small infinitesimal mass, so dm will be nothing but rho into dv, because rho cannot be d rho. Correct. Rho is a constant. So it's dm is equal to rho into dv. Now we know that what is the volume of disk. The general volume of disk for any radius r is pi r square h. So therefore dv will be equal to 2 pi r into h into dr. I hope it is constant. It is agreed by you, as the value of r will only vary. So therefore it is 2 pi r dr into h. Fine. So now we know the value of dv. So we can directly put this in this equation. So we'll get dm is nothing but equal to 2 pi hr into rho into dr. I think so. This equation is clear to you. So let us write this as equation number 1 and directly put it into this equation. So if you put it into this equation, what we will get basically, and let's integrate it also. So it's integration of di is equal to integration of this rho into 2 pi hr dr into r square. Let's put all the constants outside the integral. If you will do that, we will only get the integration as integration r cube dr. What will be the limits here? As you can clearly see, so basically what we are trying to do, we are trying to integrate, or basically we are trying to add all the small disks infinitesimally going from 0 value of radius to capital R value of radius. So therefore the limits will be 0 to capital R. Now just simple mathematical analysis is being done here. So basically you are trying to separate or segregate or basically cut all those numerators and denominator which have the same parameter. After this complete calculation and also integration r cube dr is r to the power 4 by 4, we will get I is nothing but equal to mr square by 2. Okay. So that's how you basically calculate the moment of inertia of a circular disk of radius r. Now look at this concept very carefully. Okay, just give me 1 minute. Okay, so till now basically we have understood the thin circular ring, that is mr square. We have understood thin rod of length L. We have understood thin circle, so basically circular disk of radius r. Right. If you look at the derivation, you can clearly see that we have also estimated, or basically we have also taken into account the height h of the disk. Correct. If you see clearly, the value of h, no matter whatever this be, h is getting cancelled. That means what we can also say, that for a solid cylinder also the same derivation can be used. Only this time the value of h will be very high as compared to circular disk. That's why you can see clearly that the moment of inertia of a circular disk and the moment of inertia of a solid cylinder are same. Okay, so I hope this concept is clear to you. That's why I was also saying that there is no need to do the complete derivation again, because the same derivation can be applied for solid cylinder also. Okay, the same concept you can also apply in this thin circular ring also, as thin circular ring was having mr square, hollow cylinder is also mr square. Why? Because the complete, so here what we can basically say, we can assume this amount as dm. This as dm, here we assume this small amount as dm. correct? So if you basically integrate it, you will get the mass as m, because the complete mass dm is lying at a distance r. So you can again see that mr square and mr square is same. So that's why there is no again a reason to calculate this or derive this moment of inertia. But even if exam this comes, you can assume you can basically write this properly. Just make a diagram which is looking like a cylinder. It has a height h which is very very greater than as compared to your circular disc or thin circular. So that's why. So basically we have indirectly covered this 6 and 7 also. Okay. And 3, 2 and 5 will be explained to you in subsequent part. Just after this, when this complete concept is clear, we'll move on to those theorems, and we can directly understand. This is very easy. We can directly understand how these things come. Fine. So that thing being said, now let us look at the final derivation we are about to do, which is about a solid sphere of radius. Okay. So please pay attention, because this is the most tricky which the thing can come as far as the basic moment of inertia are considered, right? So let us try to understand this also and then move on. Okay, so let me just write. So it's a solid sphere of radius capital R. Okay, so let us try to calculate the moment of inertia of a solid sphere of radius capital R. Okay, so let us assume this time what is happening. Just understand the complete analogy. Okay, let us assume this is your radius, this is your sphere, correct? Let me just make some dashed lines. Let us say this is your x-axis, so that a diagram can be understood as some sort of your this sphere way, right? Because it is quite tricky to make a circle and assume that concept to be a sphere. So let us assume we take a very small mass dm, right? So what will be this basically, if you can make me understand? So if I take this as my mass dm here, if you see very clearly, let us suppose this has a radius of y and this has a thickness which is dz. Why I took dz? Because we are moving in z axis here. So that's why I took this as dz. Okay. So let us assume this to be my infinitesimal mass here. Okay. So if you see this at this very very clearly, you can see that this is nothing but your circular disc, right? Here for a solid sphere, the infinitesimal mass can be considered, or basically is considered as a circular disc. Can you tell me the moment of inertia of this circular disc? Quite clear, it's nothing but mr square by 2. But here your m and r value will change. Okay, so I hope this concept is clear. Now let me just write it. So what will be your di? Let me write it clearly. So what will be your di? Your di will be nothing but equal to so it's nothing but dm into what will be radius? Radius will be y square by 2, right? So mr square by 2. So I just wrote mr square by 2 here. Fine. So first understanding of di is clear to you. So basically this is the infinitesimal moment of inertia of a circular disc which is being used to calculate the moment of inertia of a solid sphere. Clear? Now let us move forward. Now in the place again, just using the concept which we also understood in the previous concepts also. So basically what is rho? Rho is nothing but mass by volume, correct? So this can be written as nothing but m by 4 by 3 pi r cube. Clear? So let us do the same. So basically what will be m here? M will be nothing but rho into 4 by 3 pi r cube, correct? So what will be dm here? Dm will be nothing but equal to rho into 4 pi r square dr. I hope it is clear, because 3 and 3 gets cancelled. So the thing which is remaining is 4 into pi r square dr. Right? Now this is the one concept. Now let us, so this is just a concept being made. Now let us try to move again with this concept here. Okay, so look at this very very clearly. Okay, so here I can write this di as nothing but equal to your y square by 2 into rho into dv. Rho into dv. Correct? Now look at this dv very carefully. Look at this dv. What will be dv here? dv is basically the volume of the infinitesimal element we took. What is the infinitesimal element we took here? It is a disk. What is the volume of this disk? Don't look at dv, just tell me what is the volume of this disk. So if I look at this very, very carefully, because this is the only concept why I made this two different DMs. So just look at it. So it will be nothing but rho into, please understand, it's pi y square, that is the area of the disk, into the value of z, that is dz. Don't look at this tag, this thing which is written in a random rigid this general shape here. It is dm pi into pi rho 4 pi r square dr. Just look at this circular disk which is drawn here and try to calculate its dv. If you look at it very, very carefully, this is nothing but it's a very small disk which is having a thickness which is dz. Correct? So that is how you should understand this concept here. So every time you cannot just put dm is equal to rho into 4 pi r square dr. Okay. So if I also made you understand why I'm not using this, if you can understand it by own, this is very, very nice. But let me just try to explain you why this dm is not same as the thing we just calculated on the left hand side. So what we basically did on this right hand side was we did rho is nothing but equal to mass by volume, which is nothing but m by 4 by 3 pi r cube, right? So what we are basically doing, let us suppose this is the complete sphere. Let me make it like this. If this is the complete sphere, this dm is for this very, very small volume of sphere. This is not for this dm. I hope this is clear to you now. Okay, so this dm is, let us suppose we take a very, very small r value. Let's say this, let's say I zoom this. So basically this sphere is nothing but having a value of radius r, right? Which is, and this thickness can be said as dr. So then we can basically say that dm is nothing but equal to pi into rho into 4 pi r square t. So because there is a change in the infinitesimal element mass we took here, that's why we cannot use this concept which is basically written here. That is dm is equal to rho into 4 pi r square t. Fine. So that was just an analogy I just tried to make to you so that you can understand basically what is happening here. So basically in this concept, this is not required. So let me just rub it so that I can get more space. So people may just approach it like this also, but this approach is not being utilized here. Okay, so basically till now what we basically got, we got pi y square by 2 into rho into pi y square dz. Fine. Now let us try to just integrate it and then find the results here. Okay, so let us do it. So here integrating, we get integration of di is basically equal to, let me put all the things which are constant. So it's rho into pi by 2 outside, integration of y to the power 4 dz, right? Now look at this value of z very carefully. What is the complete range of z? If you look very closely, it will start from this location and end at this location. So it is nothing but minus r to plus. Correct? So I hope this concept is clear to you. Now what we basically need to do, we know that y to the power 4 is not a constant. This value is also varying. But this value we need to conserve in such a way that this is some sort of function of z. We know that this is a function of z, but we need to convert it into some function of z. Okay. So look at this very carefully now. So let us suppose that this is your y. Correct? It will be at some depth z. Correct? So let us suppose this is at depth z we are talking about. In all the cases, anything which is from center moving towards the corner will be capital R. So you can see clearly this is nothing but your Pythagoras theorem being applied here. We can basically say what is your y square? Y square is basically r square minus z square. Correct? So I just use simple Pythagoras theorem here. So it's nothing but using Pythagoras theorem. Pythagoras theorem. Okay, why we are doing this? We are basically doing this because as you can see that the integration to be performed is a function of dz. So basically we need this y to the power 4 in some function of z so that we can basically do the integration. So therefore what we can write here, we can basically write rho pi by 2 integration of minus r to r into capital R square minus z square whole square dz. I hope it is clear. In the place of y square, I just wrote this equation which I just got. Let us write this equation number 1. Fine. So now you just need to solve this. So I'm not doing the integration here. I'm just telling you how this integration is performed. So basically what will you do here? So it's nothing but r to the power 4 plus z to the power 4 minus 2rz whole square. Correct? So and into dz. Correct? So r square dz will give you r to the power 4 z. Similarly, z to the power 4 will give you z to the power 5 by 5, and minus 2 r square z square will give you minus 2 into r square into z to the power 3 by 3. In the places of z, on the z, we'll basically put minus r and plus r. After doing the complete calculation, just I am leaving the final integration because it's a little time taking here. I can make you understand more easy, more physics concepts here. So I'm just leaving the integration. I highly suggest to solve this integration. If you solve this integration, you will get the answer as 2 by 5 mr. Fine. So that's how you basically get the value of moment of inertia as 2 by 5 mr square. So that's how you calculate the moment of inertia of a solid sphere. Fine. So just iterating everything what I just explained to you so that you can understand it clearly. So basically we first wrote di is nothing but equal to dm into y square by 2, where our infinitesimal mass was basically a circular disk which was having a depth of dz and radius of y. So basically what is di? Di is basically in the place of dm we can write rho into dv. So if you look at this dv very clearly, it is nothing but the volume that this circular disk attains or captures. So it is nothing but pi y square into dz. I just wrote that concept here. This y square and this y square gets y to the power 4 dz. As the integration to be performed is in respect to z, we need to convert this y to the power 4 in terms of z. Now using a simple concept of Pythagoras theorem, we can say that if this is y and this is z and this is r, we can write y square is nothing but r square minus z square. Putting this value of y square here, so y square whole square will give you r square minus z square whole square. What will be the limits? As you can see clearly, dz lies for minus r to plus r to convert this to cover this complete solid sphere. Hence we can write rho pi by 2 integration minus r to plus r, and I just use a square minus b square a minus b whole square property here. That gives me r to the power 4 plus z to the power 4 minus 2rz whole square dz, and therefore when we just simply integrated, you will get the answer as 2 by 5 mr. Hence what is I? I is basically 2 by 5 mr square. Fine. So I hope this concept is clear to you. So basically just look at this diagram once again, just look at this table once again. So first of all, what was thin circular ring? I explained you what is thin circular ring. Then just ignore the second part for now. Then the third is your thin rod length, that is ml square by 12. We basically derived it in ml square by 12 in the last lecture only. We have revised this concept also. Then next is your circular disc. So circular disc also we have derived, that is mr square by 2. The next concept is regarding your circular disc with diameter. We'll understand this in some next lecture, or in this lecture only, after we have completed the understanding of your new results, which is the theorems related to moment of inertia. Then the next is your, which is the next is a hollow cylinder. We understood how hollow cylinder can be understood from the derivation of your circular ring. So it's mr square. Then next is your solid cylinder of radius r. So we understood this also. So basically h value is omitted. So we can directly write the moment of inertia of a solid cylinder also as mr square by 2. And finally, we have also derived the moment of inertia of a solid sphere of radius r, which is 2 by 5 mr. So we basically know everything. We have concluded everything, how these complete formulas came. Fine. So that thing being said, now let us move forward. I think I have explained all of these. So first for your thin circular ring, so we got this. So it is nothing but I is nothing but equal to mr square. Correct. And now let's take a rigid massless rod of length with a pair of small masses rotating about an axis through the center of mass perpendicular to the rod. So each mass is embedded at a distance of L by 2. So how we'll calculate it? That is nothing but integration is nothing but equal to summation of integration of both these two masses. So for the first mass, it's mr square. So it's m into r square plus again m into r square. Correct? So it is nothing but m by 2 into L square by 4 into 2. Correct? So 2 getting cancelled. Therefore, our moment of inertia becomes ml square by 4. Correct? So basically, I assume this to be your mass 1 or I1 and this to be 2. So basically, we sum both of them and finally got the moment of inertia is ml square by. Okay, so that is very simple integration. That is very simple derivation. Nothing typical in this. Fine. That thing being said, now let us move on to the next concept to be understood here, which is I think that is radius of gyration. Yes, fine. So let us start a new concept. I will just try to explain to you what is radius of gyration, and then we can understand it at much more clarity in the next class. Okay. So let me first convey you what is radius of gyration. So first of all, a concept that it is related to the moment of inertia and total mass of the body. So it is related to the moment of inertia. It is related to moment of inertia and the total mass of the body. And the total mass of the body. Fine. So it is related to the moment of inertia and total mass of the body. Now let me just explain you. Let me first define the radius of gyration and then I can refer to whatever concepts I need to convey to you. Okay. So definition. So basically the radius of gyration of a body about an axis may be defined as the distance or is defined as the distance from the axis of a mass point whose mass is equal to the mass of the whole body. Whose mass is equal to the mass of the whole body and whose moment of inertia is equal to the moment of inertia of the body about the axis. So, and whose moment of inertia is equal to the moment of inertia of the body about the axis. Okay, so basically what is radius of gyration? The radius of gyration of a body about an axis is defined as the distance from the axis of a mass point whose mass is equal to the mass of the whole body and whose moment of inertia is equal to the moment of inertia of the body about the axis. Okay, the definition can be quite tricky. Let me try to explain to you using one of the diagram. Okay, so please remember, let us take this case into scenario only. Example. So let us take this to be your example here. So let us assume this to be your rod which is moving with some omega. Here, what is your moment of inertia? We know moment of inertia is nothing but equal to ml square by 12, where L is the length of the whole body. Correct? So therefore, the derivation of radius of gyration just simply states that write this as equal to mk square, where k is the radius of gyration. So basically, what is the value of k you get? The value of k you get is basically L upon root 12. Correct? So this L upon root 12 is basically called as your radius of gyration of the body. So we can basically say that this mass less this rod is basically equal to some mass capital M located at a distance of L by root 12 and is rotating about an axis omega. So I hope this concept is clear to you. So basically that is the analogy being done. So this is your radius of gyration. So this is nothing but your equal to Q. Okay, so that's how the radius of gyration has been explained. Right. So that thing being said, let me first explain to you. So let us calculate the moment of inertia of radius of gyrations of all these and then move forward. Okay. Or let us close the session because I think the time is completed. The next concept requires a lot more time. So let us calculate the radius of gyration of each of these quantities and then we can move forward. So the radius of gyration for this will be equal to what we basically need to do. We just need to equate it with mk square. So what is the radius of gyration here? Radius of gyration is r. Fine. Moving forward, what is the radius of gyration of your next quantity? So it is just equated to mk square. So therefore what you get, k is nothing but equal to r by root 2. Right. Again equated to mk square. So what is the value of k? K is basically equal to L upon root 12. Again it equated to mk square. So basically what we get, k is nothing but equal to r by root 2. Equated to mk square, what you will get? You will get k is nothing but equal to r by 2. Equated to mk square, what you will get? K is equal to r. Equated to mk square, what you will get? You will get k is equal to r by root 2. Right? Equated to mk square, what you will get? You will get k is nothing but equal to r by root over 2.5. So that's how you can understand the concept of radius of gyration. So basically what is happening, let us suppose we need to understand this for a circular disk, let us suppose. So this circular disk is nothing but analogous to a mass m, or not a mass small m. Basically it is analogous to a mass capital M, which is same as the mass of the circular disk, rotating with a velocity omega, rotating with the same angular velocity omega at a distance of k, which is equal to r by root 2. Right? So then the moment of inertia of this mass capital M will be same as the moment of inertia which is offered by a circular disk of radius r. Okay, so that is the complete concept of, or the basic crux of your radius of gyration. So radius of gyration is basically used for different purposes. We'll try to understand those particular points. Just 2-3 discussions are to be done regarding the understanding of this moment of inertia and your radius of gyration. So we'll try to understand those concepts in the next lecture, and then we will move on to the further concept of moment of inertia, which is basically understanding the two theorems, which are theorems of perpendicular and parallel axis, where we can basically understand what is happening in this 2 and what is happening in this 5. Okay, we will understand more general terms, we'll understand more concepts also, but generally we will basically understand all those moment of inertia which are written in this table. Right. So that thing being said, let me stop the discussion here only. So we have completed with the radius of gyration, and I have basically derived all the quantities and explained to you all the derivations of different moment of inertia. Right. So that thing being said, let me stop the discussion here. So the course progress for you, we have completed with the introduction, center of mass, motion of center of mass, linear momentum of system of particles, vector product of two vectors, angular velocity and its relation with linear velocity, torque and angular momentum, equilibrium of rigid body, and currently we are on the 9th topic, that is moment of inertia. A little bit discussion is being left, and then we will move on to 10th concept, that is theorems of perpendicular and parallel axis. After that being done, we'll move on to 11, that is kinematic or rotational motion about a fixed axis, which is basically the analogy of the linear or translation motion to your rotational motion. So all those kinematics equations will be derived again, or basically will be put analogous to the translation motion, and different concepts will be understood there. Different concepts which are referring to the same concept which you have learned, such as omega, alpha, t, etc. Fine. That thing being said, we'll move on to one of the interesting concepts regarding the dynamics. of rotational motion, angular momentum in case of fixed axis, basically usage of your conservation of angular momentum, and finally rolling motion. Fine. So let me stop the discussion here only. Thank you for listening. Please try to solve all these, try to derive all these moment of inertia so that you can understand this at a much more clarity. And thank you. We'll meet in the next lecture.